Hello everyone, I am a recent BS in EE graduate from the University of Kentucky, and I will be starting graduate school there, the University Scholars Program, next semester. This is my work with electric load forecasting and smart homes. In this work, 3 years of public data from 2 smart homes, H1 and H2, and a public dataset managed by Electric Power Research Institute were processed from the 15-minute resolution to an hourly time step. The summer daytime hours, 6 a.m. to 9 p.m., were isolated as these are the higher use times of day for residencies. An LSTM encoder-decoder model shown on this slide was trained on the summers of 2018 and 2019 to predict the summers of 2020 in 3 categories. Total HVAC and PV power in kilowatts, which is the Y of T on this diagram. The model used includes 2 layers of LSTM long short-term memory model cells built in Python using Keras and takes 3 of the prune days from 6 a.m. to 9 p.m. or 48 hours of previous power usage, as well as 2 days of previous weather data and 1 day of a perfect forecast. The perfect forecast is the future weather data to establish the relationship between the usage patterns and the weather at that time. The input X per output are listed here, with the outdoor temperature difference indicating the magnitude difference in the temperature indoors and outdoors. This indicator serves to tell the model when the HVAC system will operate. An example week of predictions for total, HVAC, and PV are shown on this slide for both H1 and H2. The different patterns of the 2 houses can be seen, highlighting the variability between residencies due to differences in appliances and human behavioral patterns. The LSTM model was trained separately for both house predictions to account for this. The total predictions are the most influenced by human behavior, and the LSTM models performed very similarly with about 10% normalized RMSE error. The HVAC systems also had different patterns, but the normalized RMSE for H2 was lower than H1. However, from looking at the trends, from visualizing the predictions, H1 matches closer than H2 to the actual consumption the majority of the days, but there are some days that are outliers which pushed this normalized RMSE up. The PV model performs better on H1, as well as there are less sharp declines in the measured data from either shading or other interferences from the generation in H1 than H2. To better characterize the performance, I've plotted the distribution of the errors for each predicted time step across H1. The HVAC and PV model showed a strong cluster of error around 0, while the total is more distributed in a normal bell curve shape, another indicator of the influence of human behavior. The second part of this work was to predict a desired profile, of which I have selected the HVAC load from only the total kilowatt usage data for H1, as would be available from smart meters. I propose a novel method using the relationship of the total usage for the home to the outdoor temperature, commonly called the V-curve. As this house is in Florida, only half of the V-curve is present due to mild winter climate. I've selected the temperature for the minimum HVAC load, TM HVAC, to be 18 degrees as shown by the star in this graph. The next step is to train the LSTM model on the total load, and then in the test set, replace the temperature values in irradiance with the TM HVAC and 0 watts per meter squared as if it was nighttime, so that the model predicts the base load for the house as if the HVAC system was not running. From there, a subtraction can be performed to separate the HVAC load from the measured or forecasted total. Using this method, I have obtained a strong correlation between the measured and separated HVAC, as shown here and in these charts. In conclusion, the LSTM encoder-decoder model, developed specifically for residential load predictions, performed satisfactorily, with the most frequent error being near 0 for PV and HVAC. The novel HVAC separation method, presented based only on smart meter data, performed as well as forecasting from historical measured data from a dedicated circuit, HVAC, and may represent a significant contribution to the field deployment of smart meters. The support of my advisors in the NSF is gratefully acknowledged.